Hello friends, today's question. A binary star consists of two stars A 2.2 ms and B mass 11 ms, where ms is the mass of the sun. They are separated by a distance d and are rotating about their center of mass, which is stationary. The ratio of total angular momentum of the binary star to the angular momentum of the star B about the center of mass is. So we are given two stars A and B, and respectively they are rotating about their center of mass. Okay. And let us suppose we have a star A whose mass is given as 2.2 ms, and we have a star B whose mass is given as 11 ms, and they are rotating, and they're separated by a distance d. Let us suppose this is distance d, and they are rotating about center of mass, and let us suppose this is the center of mass somewhere here. So we have to find out the ratio of the total angular momentum to the angular momentum of star B. So obviously the total angular momentum will be equal to angular momentum of star A rather, plus angular momentum of star B, and we are going to further solve it. So we already know that first of all we are going to find out what will be the center of mass of the system and then solve it. Okay. So let us find out. Determining the center of mass of the system means both A and B. Determining center of mass of the system, and for this we already know the formula. The center of the mass of the system, let us suppose that is given as R center of mass. This will be equal to mass of star A multiplied by distance of star A plus mass of star B multiplied by distance of star B divided by mass of A plus mass of B, where this RA is the distance of star A from center of mass. RB is also distance of star B from center of mass. So this is our RA and this is our RB, and MA and MB are respectively the mass of star A and star B. You can say MA is mass of star A and MB is mass of star B, and it is given, or we can say from this we can say that the distance between the two stars is given as d. The distance between star A and star B is given as d, which will be equal to RA plus RB. And from here we can say that, okay, let us keep this equation, and it is also given that the center of mass is stationary. So we can say that for center of mass to be stationary, we can say that mass of A multiplied by R of A is equal to mass of B multiplied by R of B. So here let us suppose we find out R of A, which will be equal to mass of B, R of B divided by mass of A. Now substituting this value of R of A in the distance equation, let us call this equation number 1. Therefore, equation 1, we get D is equal to, we have MB RB divided by MA plus RB. So taking RB as common, we get this as RB, and we have MB divided by MA plus 1, and from here we can say that our RB will be equal to D divided by mass of star B, mass of star A, and plus 1. Now substituting the value of mass of B star as well as A, D as it is, mass of B is given as 11 ms, mass of A is given as 2.2 ms, and plus 1. This will be equal to D upon 5 plus 1, so we get D upon 6. So we get RB is equal to D upon 6. Now we can find out RA. So RA will be equal to D minus RB, which is equal to D minus D by 6, and comes out 5D upon 6. So we found out RA as well as RB. Now next we are going to find out the angular momentum. Calculation of angular momentum. Of angular momentum. So we can say angular momentum of, let us suppose that is represented as L. Angular momentum of star, let us suppose is given as L. So this will be equal to mass into velocity and multiply by the distance, which is R, and we know the relationship V and omega R. We can say, but V is equal to R omega, so therefore we get L will be equal to M omega R square. Now let us modify this formula for both star A as well as star B. So we say angular momentum for star A let us that given as LA, so it will be equal to mass of A, angular frequency of A multiplied by RA square. And for omega A, let us suppose represented as simple omega. Therefore we get, substituting the respective values, we get LA, mass of A is given as 2.2 ms, omega A we say, let us suppose is omega, and RA we found out is given as 5D upon 6 whole square. So this comes as 2.2 ms, and we have 25 d square upon 36 multiplied by omega. So we found out LA. Similarly, the angular momentum of star B. Angular momentum of star B, let us suppose that is LB. So we have here MB, omega B and RB square, and once again omega B is equal to omega with the same angular velocity. Therefore we get that LB will be equal to mass is 11 ms and omega, and RB is our d upon 6 whole square. So this becomes 11 ms multiplied by, this will be d square upon 36 multiplied by omega. So therefore total angular momentum means LA plus LB. Total angular momentum, that is L will be equal to LA plus LB. Substituting value of LA and LB, we get L is equal to, we have 2.2 ms and 25 d square upon 36 omega plus 11 ms, and we have d square upon 36 omega. So taking common as d square upon 36 from, and therefore we get this as 2.2 ms and multiply by 25 plus 11 ms and taking omega as also constant. So we get total angular momentum L will be equal to d square upon 36. This comes as 66 ms and omega. So this is our total angular momentum, and this is our angular momentum of B, star B rather. So we are supposed to find out ratio of total angular momentum to the angular momentum of star B. Therefore, ratio of total angular momentum to angular momentum of star B around center of mass, to angular momentum of star B about center of mass. This will be equal to L divided by LB. L is our, right on next page. So we are supposed to find out L upon LB, and angular momentum of L is our d square upon 36 multiplied by 66 ms omega divided by, we have d square upon 36 multiplied by 11 ms and omega. So these terms cancel out, and this comes as 66 by 11. Therefore, we get ratio total angular momentum to the angular momentum of B is equal to 6. This is equal to total angular momentum divided by angular momentum of star B about center of mass. So it comes as 6. So this completes the question. Thank you.